Hello everyone, myself Sourav Kuila, Assistant Professor in Physics, School of Applied Science and Humanities at Wilde Institute of Technology. In this video, I'm going to discuss about magnetic properties of material. So, here in these slides, there are some images of electrical and electronic appliances. First, here you can see the ray diagram of generator and motor, where magnetic materials are very much likely to used. Without this magnets, it will not work. In another image, there is a image of MRI, that is in biomedical application which it is used. In MRI, a very high magnetic field is usually used to scan human body. Okay, and here these are the images of different kind of sensor, magnetic sensor, motion sensor, position sensor. Okay, so in these sensors also magnetic materials are used. Here, a very much well-known image of our uh, regularly used memory devices like memory chip, RAM, ROM, hard drive, everywhere. The magnetic memory devices are made by use magnetic materials. The last image, it is of uh, communication system. Okay, the this first one is the transmitter of signal, and second one is the receiver of the signal. In both cases, these magnetic coils are used to transmit or to receive the signal. So we can say in every corner of our technology and engineering, every corner, magnetic materials are heavily used. So it is very important to learn about magnetism and magnetic material. Okay. So first we will see what is magnet. All of you have some knowledge about magnet. That magnet is a particular type of specific type of material which attract iron, nickel, cobalt, that kind of special metals. Or magnetism is the force that exerts by a magnet. Magnet usually has two poles, north pole and south pole, and the similar pole or the same pole always repels and the opposite poles always attracts. Okay, so first, the origin of magnetism lies in the Oersted experiment. The Oersted experiment is shown in this image. Here you can see the first image, that a magnetic needle is kept adjacent to a current carrying wire. The first one, there is no current flowing through the wire. That's why there is no deflection in the magnetic needle. In the second image, you can see while a small current passing through or flowing through the current carrying wire, there is a small deflection in the magnetic needle. And the third one, if the current direction reversed, then also the deflection of magnetic needle also get reversed. So in this experiment, Oersted concluded that the current carrying wire always produced a magnetic field surrounding it. So that's why that magnetic field deflect the magnetic needle. That means magnetic needle always get deflected by some magnetic field. So therefore, it is concluded the magnetic field produced due to flowing through current carrying wire. While a current flowing through a wire, there is a magnetic field produced or created its surroundings. Okay, so that magnetic field due to a current carrying wire was first evaluated by Biot-Savart law. There is a Biot-Savart law. It is very well known formula. So by using this formula, one can evaluate the magnetic field and its direction. Here, the magnetic field is always perpendicular to the direction of current and the direction of the point uh, from which, uh, I mean, uh, the point the distance between the current carrying wire and the point at which you are trying to measure the magnetic field. Okay, that are so direction of magnetic field is cross product of current direction and the direction of the point from the current carrying wire. Okay, so it is famous the right hand thumb rule. You can see in this image that the direction of magnetic field in a current carrying wire is in a circular path, at a closed circular path. Okay, so if we bend the current carrying wire into a circular loop, in this image you can see in this circular loop the direction of magnetic field is showing like in this, like these arrows. Okay, so direction of magnetic field will be like this. If you uh, replace a number of turns instead of a single turn, there a number of turns will the magnetic field due to a n number of turns will be like this in this image. Okay, this is called solenoid. Okay, so in solenoid magnetic field you can see it enters from one side and getting out from the opposite side, and the magnetic field lines are almost parallel inside the solenoid. Okay, so if you compare with a bar magnet, here let's see in bar magnet all the magnetic field lines get into at south pole, and the magnetic field lines are coming out from the north pole. And comparing this bar magnet with the solenoid, you can say the north pole is that pole for a solenoid that from which the magnetic field lines are coming out, and the south pole is that point or that phase into which magnetic field lines are getting into the solenoid. Okay, so we can say we can mm, we can say the north pole, there is a convention that north pole produced when the current flow anti-clockwise in a circular loop. You can see in this image that north pole is defined like this, that when the current flow in a circular loop anti-clockwise, it creates north pole. I mean that phase is south pole, and the just opposite phase of the current carrying loop, circular current carrying loop, if the current flowing in a clockwise direction, then it will called south pole. Okay, so one phase the current will flow in clockwise direction, and other phase current will flow anti-clockwise direction. So one phase is south pole and the another phase is north pole. So this current carrying loop always created a magnetic dipole. One side is north pole, one side is south pole. Okay, so a current carrying loop is always a magnetic dipole. Okay, now these magnetic materials in our world mainly classified in three main types. One is diamagnetic material, one is paramagnetic material, and one is ferromagnetic material. Diamagnetic material, we all know that when the material repulse from the magnetic field weakly, then these materials are called diamagnetic material. These like copper, silicon, inert gas, these are the diamagnetic material. Paramagnetic material attracted to the magnetic field but very weakly. Example, um, aluminium, oxygen. And ferromagnetic material, the special kind of, that is iron, nickel, copper. These materials are strongly attracted to the magnetic field. Okay, and it later found that then in diamagnetic material there is no permanent dipole. no permanent dipole. If you don't apply any external magnetic field, there will be no permanent dipole. Okay, there will be no not polar south pole. In paramagnetic material, there is dipole very small. Okay, but they are randomly oriented. Here in this image, you can see in diamagnetic material there is no permanent dipole without application of magnetic field, and paramagnetic material there is no there is dipole, permanent dipole, but they are randomly oriented. And in ferromagnetic material, they made the group. I mean, they made the domain. Domain means in a particular region, all the dipole moment directed towards the same direction. Okay. In another region, they are also in in another region of the material, the dipoles are oriented in a another direction, but they all directed in the same direction. I mean, first region or first domain, the direction of first domain is different to the direction of second another domain. Okay, but the net dipole moment when the applied magnetic field is zero is also zero. So in this image, you can see that in for diamagnetic case, when you applied the external magnetic field, the dipole moments are aligned just opposite to the applied magnetic field. Okay, that's why it's repulsed from the applied magnetic field. So this type of material called diamagnetic material. You can see here that it is called chi m is less than 0, that is chi m is negative. Chi m is the parameter which defines how easily, or you can say how easily a magnetic material can be magnetized. When you apply the external magnetic field, how easily you can magnetize a magnetic material, it is called, that parameter is called chi chi m. Okay, it is chi m means magnetic susceptibility. Chi m is called magnetic susceptibility. In case of diamagnetic material, magnetic susceptibility is negative. You can see because the direction of magnetic dipole moment is opposite to the applied magnetic field. In paramagnetic case, you can see the application of magnetic field aligns the um, dipole moments, but very weakly. The chi, the magnetic susceptibility, is positive. Okay, but in ferromagnetic material, you can see the chi is very greater than 1. The chi m is very strong, very high. That means ferromagnetic materials are very easy to magnetize, but paramagnetic material and diamagnetic material, it is chi m is very small. Okay, that's why it is very hard to magnetize it. Okay, so in ferromagnetic materials, when you apply the magnetic field, the domains are aligned to the applied magnetic field. Okay, now in case of ferromagnetic material, that I said, the application of external magnetic field makes all the domains align towards the applied magnetic field. So when you don't apply any magnetic field, you can see in this image, if all the domains are oriented randomly towards the random direction. Now you applied some uh, magnetic field. Okay, the first one is the origin, when you applied zero magnetic field and the net magnetic moment is zero. And it is the x-axis. In the x-axis, there is applied magnetic field, and in the y-axis, the magnetization. Magnetization is the measure of the magnetic moment of the material. Okay, magnetization defined as the net magnetic moment per unit volume. The net magnetic moment per unit volume is called magnetization. Okay, so how much magnetic moments are developed in the material is called magnetization. So first, if you apply no magnetic field, there will be no magnetization. It is zero at the origin, because the all the domains are randomly oriented. Now you are applying external magnetic field. So while you are applying external magnetic field, domains are trying to align to the direction of applied magnetic field. And when you increase the external magnetic field, it will, the magnetization will increase, and after a certain application of external magnetic field, there will be all domain will aligned, okay, and it will get saturated. The magnetization gets saturated. All the domain get aligned means there is maximum magnetization. After the increase of after that increase of external magnetic field will not increase the magnetization. So it is called saturation magnetization. Okay. Now you decrease the magnetic field, external magnetic field H, and when you decrease the magnetic field, external magnetic field to zero, the magnetization will not get zero in case of ferromagnetic material. Okay. This is called remnant magnetization. When the applied magnetic field is zero but magnetization is not zero, it is called remnant magnetization. Okay. Now to demagnetize means you have to make the net magnetization of the material to zero. To demagnetize the magnetic material, you have to decrease, you have to apply the external magnetic field in the opposite direction. So when you applied a reverse magnetic field, then after a certain value it get demagnetized. That means the magnetization will be zero, and again all the domains will oriented randomly. Again, if you increase the applied magnetic field reversely, then after a certain application of magnetic field, reverse magnetic field, you will get a similar saturation, magnetic saturation, that is the all the magnetic domain will align but in opposite direction for the first time, for the first scenario, with respect to the first scenario. Okay. Then again, if you decrease the reverse magnetic field, it will gives you a similar kind of pattern or the similar kind of graph in with respect to the first curve. Okay. So this curve is called magnetic hysteresis. Hysteresis means that the dependent variable magnetization will not follow the independent variable H. Okay, here you can see when H is zero, magnetization is not zero. That means magnetization and applied magnetic field does not follow each other. Okay, so that's why it is called hysteresis. And due to this hysteresis, you can see a very good hysteresis loop. This kind of loop is called hysteresis loop. Okay. In case for paramagnetic and diamagnetic material, there will be no hysteresis loop. That means in those case, magnetization follows the applied magnetic field. It will looks like linear. Okay. So this property of ferromagnetic material, this hysteresis property is in ferromagnetic material is used in memory devices. That means you applied zero magnetic field when you switched off the uh, device, or when you switched off the applied magnetic field, there will be a retention of magnetization. That means the memory is still on. I mean, the memory is still there when you switched off. Okay. In application of zero magnetic field, there is the retention of some memory. Okay, so this property is used in magnetic random access memory devices. Okay, so we already said that when H is 0, the retention of magnetization is called magnetic remanent magnetization or remanence. This one is a saturation magnetization, and the point at the point when the reverse, due to application of reverse magnetic field, when the magnet got fully demagnetized or the magnetization is 0, this point is called cohesive field. This field is called cohesive field. Okay. So depending on this cohesive field, depending on the value of cohesive field, we classified the ferromagnetic material in two categories. One is soft ferromagnetic material, another is hard ferromagnetic material. In soft ferromagnetic material, you can see the cohesive field is very small. Okay, that is, you can demagnetize the material very easily. Very small application of reverse magnetic field, you can demagnetize the material. This type of material is called soft ferromagnetic material. But in case of hard ferromagnetic material, you have to apply a very large reverse magnetic field to demagnetize the material. Okay, so it is the hard magnetic material has very robust magnetization, and in soft it is not robust. Okay, the hysteresis area is very large in case of hard magnetic ferromagnetic material, and hysteresis loop area is very small, you can see. So ferromagnetic materials are not ferromagnetic materials are the materials which have permanent magnetization without application of external magnetic field. So this permanent magnetization can be destroyed upon increasing the temperature. So in this graph, you can see the in ferromagnetic material, if you increase the temperature, in x-axis, so if you increase the temperature, you can see the magnetization decreases, and after a certain point, it get paramagnetic. So from ferromagnetic to paramagnetic. Okay, it became ferromagnetic to paramagnetic after a certain temperature increment. Okay, this certain temperature is called Curie temperature. So Curie temperature is the temperature above which ferromagnetic material get paramagnetic material. Okay, so this ferromagnetic the ferromagnetism or ferromagnetism dependency on temperature can be expressed by this equation. This is called Curie-Weiss law or Curie-Weiss equation. This chi is called magnetic susceptibility, as I told before, and C is the capital C. This C is the Curie constant. T is the temperature, absolute temperature, and Tc is called Curie temperature. Curie temperature means here is theta C is showing as Tc. The Tc is the Curie temperature. Okay. Now we can see here an image where a ferromagnetic material is placed in between a magnetic field. So in magnetic field, if there is no ferromagnetic material, you can see the magnetic field lines will be parallel. Okay, it's very parallel with each other. When you introduced a ferromagnetic material inside a magnetic field, all the magnetic field will try, or maximum number of magnetic field will try to get into this ferromagnetic material. Okay, so here will be a depression. You can see a depression of magnetic field lines. All the maximum of magnetic field lines will try to pass through this ferromagnetic material, because ferromagnetic material has very high value of chi magnetic susceptibility. That's why. Okay, so if we are going to measure the magnetic flux density inside the ferromagnetic material, so what we have to do? Okay, the magnetic flux density is the number of magnetic field lines per unit area. If you draw a imaginary unit area, and the number of magnetic field lines through that unit area is called magnetic flux density. Okay, so inside the magnetic material, the total magnetic flux density will be the magnetic flux density outside the ferromagnetic material and magnetic flux density due to magnetization of this material. I mean, when you place a ferromagnetic material inside a magnetic field, it will get magnetized. Okay, it will get magnetized means this will also be another magnet. Okay, so from that magnet also the magnetic field lines will coming out. So two kind of magnet, I mean two magnetic field lines will be appears. One is for external magnetic field, external magnet, the magnetic field lines due to external magnet, and magnetic field lines due to this magnetized ferromagnet. Okay, so there will be two magnet, and from these two magnet, two kind of magnetic field lines will appear. So inside the magnetic material, the magnetic flux density will be represented as magnetic flux density for external magnetic field and magnetic flux density due to magnetized material. Okay. So magnetic flux density can be represented as mu zero times of external magnetic field intensity H. Okay. Mu zero is the free space permeability. Free space permeability means how much number of magnetic field lines are uh, are passing through a material. Okay, or free space. Free space means there is no material. How much magnetic field lines per unit area is passing through. Okay, or okay, um, and BM means magnetic flux density for magnetized material. Okay, so for magnetized material, for magnetic flux density is equals to mu zero times of magnetization. Okay, M is the magnetization. So putting this value in this equation, we can have B equals to mu zero H plus mu zero M. Okay, so this magnetization is proportional to the applied magnetic field. That is, if you are increasing the applied magnetic field, the magnetization will increase. Okay, so it is represented as M is equals to chi m into H. You already have knowledge about this equation. The chi m is the magnetic susceptibility. So if you put this formula here instead of M and simplifies it, you can have this equation. Okay, and finally simplifying this equation, we can have this equation. This is the expression of mu r. Mu r means the relative permeability. The relative permeability means permeability of a material with respect to free space. Okay, so mu is the permeability means what is the tendency of a material, or what is the tendency of magnetic field lines to going through or passing through a material. Okay, so this is called relative permeability. Okay, so there are some related questions of this topic. You can practice for your preparation, and thank you.